All right, in this video, we are going to move into section 1.4 titled the matrix equation. So not a very long section in this video, but we do want to talk kind of some basics about, once again, kind of a continuation of this matrix idea. And we talked about linear combinations last time. And so in this video, how do we get into what the matrix equation is and where it can be solved and how it can be solved? So before I go into more of the details, let's kind of talk about the basics of what this equation looks like. It looks really nice, but what components are we going to be dealing with? So let's assume that if A is an M by N matrix, where we can denote the columns of A as the vectors A, A1, dot, 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 through AN. So every column of matrix A, we're going to think of those as vectors, which we talked about in the last video. And then if we let X be in the nth dimension of R, then the product of A and X, denoted A times X, is the linear combination of the columns of A using the corresponding entries in X as weights. So what you probably recall, if I look right here in the equation below, this is what we looked at last time, where we know now how to solve x1a1 plus x2a2 plus dot, 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 dot. That is a linear combination that we know we can set up as an augmented matrix. We're going to take a step back and write it in a slightly different way. How we can break this down, though, is that if we think of the A columns making up this matrix A, and then X being a column vector that we're multiplying, these will be generated in this way. Now, in this section, we're going to be going from A times X and wanting to put it into this matrix equation form, or this linear combination form, I should say. So all you have to do that is you're going to take the first entry of the column vector, multiply it by the first column of A. That gives you the first piece. Then you move to the second piece of the column of X and multiply it by the second column of A. That gives you your second piece. You continue that until you run out of entries to deal with. The number of entries in the vector X should match the number of columns in A. Otherwise, these cannot be multiplied together. All right. So as I put down here in the note, A times X is defined only if the number of columns of A equals the number of entries in X. And that should be in, not is. That's called bad typing right there. So while we're not going to solve a matrix equation just yet, let's practice doing this multiplication idea with actual numbers everywhere. So on part A, I'm asking you to multiply the 2 by 3 matrix 1, 2, negative 1, 0, negative 5, 3 by the column vector 4, 3, 7. So the first thing we always get in the habit of checking, at least for right now, is that the number of entries in X, which is 3, matches the number of columns in A, which is also 3. So we are allowed to multiply these together. So to do that, like I showed you on the last slide, you'll take the first entry of your vector, which is 4, that's this 4 right here, and you're going to multiply it by the first column of A, which would be the column 1, 0. You will add to that, take the second entry of the vector, which is 3, multiply it by the second column of A, which is 2, negative 5. And then finally add to this, take the 7, multiply it by the third column, which is negative 1, 3. As we saw in the last video, this is just scalar multiplication. So distribute your constants through respectively, and you should get 4, 0. Oops, sorry, y'all. Go away. Sorry, hit the wrong button. 4, 0 plus 6, negative 15 plus negative 7, 21. And since all of those are three-dimensional vectors, we can just add them across the first entries, second entries, etc. And so you should end up with 4 plus 6 is 10, 10 plus negative 7 is 3, 0 plus negative 15 plus 21 more should give you 6. And so we have just multiplied a matrix times a vector for the first time in this class. Now the dimensions don't have to be the same every time. Once again, I can change the dimensions of everything as long as the numbers match in the way we talked about. So what if we take a 3 by 2 matrix and multiply it by a column vector with 2 entries? So this vector has 2 entries. There are 2 columns to A. We are allowed to multiply these together. So we'll start with the first entry of the vector, which is 4, times the first column of the matrix, 2, 8, negative 5. And then we'll add to that the second entry, which is 7, times the second column, which is negative 3, 0, 2. Multiplying your constants through, you should get 8, 32, negative 20, plus negative 21, 0, 14. Add those two vectors together. 8 plus negative 21 is negative 13. 32 plus 0 is 32. Negative 20 plus 14 is negative 6. And so you just found a different vector by multiplying these together. And so while we're not going to always have numbers for everything, because we're going to have to solve for some of these unknowns, what we've done here, it's a way that you can verify your answer. Because in a few minutes, and really in future sections, your job is going to be to solve for these vectors. So once you find the vector, if you want to double check your answer, this is a way you could do that. Multiply it by the original matrix A and see if it equals the answer or what you're trying to achieve here. All right, so that leads us to the big theorem in this section, which is going to kind of connect this section with the previous 2 or 3 sections. So kind of a repetition here a little bit. If A is an M by N matrix with columns A1 through AN, and if B is in the nth dimension, then the matrix equation has the exact same solution set as the vector equation. So as we saw a few slides ago, when you multiply a matrix A times an unknown vector X and set it equal to a vector B, you are just going to get a vector equation, which is what we saw in the last video in section 1.3. The reason that's important is because in the last video, we talked about at the very end of that section that if you have a vector equation, you can solve that by setting up an augmented matrix. So ta-da! While this is something that looks a little bit different, we're not going to solve it any differently than we have done any section so far. If you have a matrix equation, you can set it up by taking the columns of A, and then at the very end, you'll put the B column to make it an augmented matrix. So one thing I want to do before we solve a problem is that you've probably realized, especially if you started watching the videos a little bit more regularly here, is that a lot of this stuff is starting to kind of get mixed up, and it means different things, but you solve them all the same. And that's kind of the key here. We're going to solve everything using augmented matrices for a lot of chapter 1. But you have to note that there are many different ways to denote an augmented matrix back in its original form. So let's use this example to kind of talk about that. This example says, express the following system of equations in the 3 ways we've talked about. What is it equivalent to as a matrix equation? What is it equivalent to as a vector equation? And then what is its augmented matrix? And we can do these in any order that we would like. What I'm actually going to do is do them in the order that we've learned them, even though that may not be the order that we're covered right here. So actually, the first thing that we learned was part C. We know from section 1.1 that we can turn a system of equations into an augmented matrix. So to do that, remember, you're going to take the coefficients of your x variables and put those in the first couple rows. That would be 1, 2, 3, 4, and then the values on the other side of the equal sign, which we call the b values, those get thrown on the end to make it an augmented matrix. And so that's the answer to part C. All right, so now what is this equivalent to as, let's see, a vector equation? So we're kind of going backwards here from what I listed here, but it's the order we learned them. So remember, a vector equation has the form x1, a1 plus x2, a2 equals the vector b. So in this case, our x's are unknown and our a's are column vectors as we saw in the last video. So this would be x1 times a1, which is the first column of A. That would be 1, 3, plus x2 times a2, which would be 2, 4, needs to equal the vector b, which is 1, negative 1. And there you go. That is your vector equation. And now the new thing today, part A, if you want to put this into a matrix equation form, all you have to do is, so that form is A times X equals B, where A is going to be the matrix of just the coefficients. Remember, A is made up from the columns of A. So that would be 1, 2, 3, 4. You multiply that by your vector X, which is just the entries of your unknowns. Our unknowns in this problem are x1 and x2. And then we will set this equal to our vector B, which is 1, negative 1. And so if I go back and circle all these in green, these three things, while different names, and really even this one up here at the top, while all four of those look different, they are all equivalent to each other. It's a system, a matrix equation, a vector equation, and an augmented matrix. And since they are all equivalent, you can pick whichever one you would like to solve. And in this class, this part C is the key. Any of those forms can be written as an augmented matrix and then solved by row reduction. All right, so let's do our first problem like this. Example 3 says, if A is the following 3 by 3 matrix, 1, 2, 1, negative 3, negative 1, 2, 0, 5, 3, and the vector B is 0, 1, negative 1. Write the augmented matrix for the linear system that corresponds to the matrix equation, solve the system, and write the solution as a vector. So the good news is what we just did the last slide is I don't actually need you to write it in matrix equation form because we just talked about that for a matrix equation, you just need to go ahead and immediately write this as an augmented matrix. So if I set up my augmented matrix, we'll use A, which is 1, 2, 1, negative 3, negative 1, 2, 0, 5, 3, and then put the vector B on the end to make it augmented. And since it's asking you to solve the system completely, you need to put this into reduced echelon form, which means you got to get it all the way down to you know exactly what the answer is. So let's do our row reduction. Our first pivot position is already good, so I just need to get rid of that negative 3 in the first column. So I'm going to take R2 and add 3 R1s to that, which means row 1 will remain the same. Row 2 will end up being 0. Negative 1 plus 6 is 5. 2 plus 3 is 5. 1 plus 0 is 1. And then 0, 5, 3, negative 1. Not the nicest numbers ever, but we can deal with these. What I'm probably going to do is I'm going to go ahead and scale the middle row. It's not going to be perfect, but at least it'll make the numbers a little bit nicer. I'm going to take row 2 and multiply everything by a fifth. It doesn't help the last number, but it does help 2 of the 3 numbers. So let's write this as 1, 2, 1, 0, 0, 1, 1, 1 fifth, 0, 5, 3, negative 1. Because in the end, I now have my next pivot position as a 1, and that makes it a little bit easier to get rid of the 2 above it and the 5 below it. So when I do that, to get rid of the 2, I'm going to take row 1 and subtract 2 row 2s. I'm going to take row 3 and subtract 5 row 2s. So the only row remaining the same is the middle one for now. Let's start with row 1. Subtract 2 times the number below it. So that's 1, 0. 1 minus 2 is negative 1. 0 minus 2 fifths is negative 2 fifths. And then for row 3, if I subtract 5 times above it, that would be 0, 0. 3 minus 5 is negative 2. Negative 1 minus 1 more is also negative 2. All right. My next pivot position is a negative 2. I would rather that be a 1. So I'm going to take R3 and I'm going to multiply everything by a negative 1/2. So 1, 0, negative 1, negative 2 fifths. 0, 1, 1, 1/5. And my new row 3 would be 0, 0, 1, 1. Last thing we got to do is eliminate the -1 and 1 above that third pivot position. So I'm going to take row 1 and we're going to add row 3. And we're going to take row 2 though and subtract row 3. So row 3 remains the same. For row 1, if I just add the numbers on the bottom, that is 1, 0, 0, 3/5. And if I take row 2 and subtract row 3, that is 0, 1, 0, -4/5. This is reduced echelon form, which is what you were trying to do. So if you kind of regurgitate what those rows are telling you, the first row says that x1 needs to be 3/5, then x2 needs to be -4/5, and finally x3 is 1. But the instructions say write your solution as a vector. So if you recall from this section, our vector x's are going to be us listing the entries of our variables in order as a column vector. So this is the general form of x. Just plug your 3 numbers in this case. So that would end up being 3/5, -4/5, 1. This is the vector of the solution to this matrix equation. All right. So to wrap up section 1.4, like I said, that's the matrix equation. I'm not going to sit here and do a bunch of these because it's kind of the same stuff over and over. But the one other thing that is in this section that's going to be important for us, especially towards the end of chapter 1, is this theorem. So there's a bigger theorem coming in chapter 2, but this theorem will suffice for what we're going to do in chapter 1. It says, let A be an m by n matrix, then the following 4 statements are either all true or they're all false. So if you can, the idea of this is that if you can show me that one of them is true, then they all have to be true. Likewise, if you can show me that one of them is false, then they are all false. So as I read through these, let's kind of see what these all are. Part A says that for each b in the nth dimension, the matrix equation has a solution. Okay, so you can find a solution of the matrix equation. Part B says each b in Rm is a linear combination of the columns of A. That makes sense. If you can solve the matrix equation, then that means that there is a linear combination from section 1.3. So that kind of makes sense why if one works, the other one does, and vice versa. Part C, the columns of A must span the entire nth dimension. And I'm going to box this one in. This is the new thing. This is why this theorem is so important right now. This is the first time we've seen that not the columns of A are going to span, or not that a certain vector spans the columns of A, that the columns of A span an entire dimension. That's unique. And then part D says A has a pivot position in every row. So in the little asterisk I put down at the bottom here is that in this theorem, A is the coefficient matrix, which means you only need the numbers that are attached to the variables x1, etc. So as you look through this, the big thing we're about to do is we're going to have to be able to show that part C is true in certain questions. Well, to do that, if you can show me that either A, B, or D is true, then C must be true. Likewise, if you can show me A, B, or D are false, then C has to be false. Now, in my honest opinion, I'm going to usually stick to doing D, because D is a little bit faster to show than A and B. And the reason being is that to show that A has a pivot position in every row, you only have to go into echelon form. A reduced echelon is not required. Versus in part A and B, sometimes to show those, you will have to go into reduced echelon form, which may require a few extra steps on your behalf. So my suggestion to y'all as a class is that if you're trying to show that the columns of A span a certain dimension, then you need to show that A has a pivot position in every row. So let's do a couple examples of that to wrap up section 1.4. Let V1 be 0, 0, 3, V2 be 0, negative 3, 9, and V3 be 4, negative 2, negative 6. Does the set of vectors V1, V2, and V3 span the entire third dimension, Y or Y not? So, as we talked about, to show that these three vectors, whatever vectors I give you, span a certain dimension, you need to figure out if the coefficient matrix made up of these vectors has a pivot position in every row. So I am going to start to write my matrix, and I'm just going to list the vectors in the order they're given. So 0, 0, 3, 0, negative 3, 9, 4, negative 2, negative 6. Now remember, we don't need reduced echelon, we just need echelon form. So the first thing I notice is that we don't want a 0 in the upper left corner. We need some number there. And the only number we have in that first column that we can move up there would be the 3. So the first thing I'm going to do is take row 1 and interchange it with row 3. So that would give you 3, 9, negative 6, 0, negative 3, negative 2, 0, 0, 4. And by luck of our draw and the problem that I picked out of the book for us to work, this is echelon form. Because remember the rules of echelon. If every pivot position is further to the right as you work your way down, and every number below that needs to be a 0. This meets all that criteria. And as you can see, there is a pivot position in all three rows of this matrix. So back to our question, does the vector span R3? Yes. Now, for the why or why not answer to this, simply because there is a pivot position in every row of A. And that's your answer. Not an over-the-top idea, but it's just a way, and that's the fastest way that you can show vectors span a certain dimensional number. So let's do one more. So last problem for this video. Let's say we have these three vectors. So I gave you three vectors again, but I added an extra entry. So V1 would be 1, 0, 1, negative 2. V2 is 3, 1, 2, negative 8. And V3 is negative 2, 1, negative 3, 2. Do these three vectors span the entire fourth dimension? So they're all four-dimensional vectors, but do they span the entire fourth dimension? Okay, let's figure that out. Same idea. We're going to set up a matrix with these as columns. So 1, 0, 1, negative 2, 3, 1, 2, negative 8, negative 2, 1, negative 3, 2. And we want to get this into echelon form. Well, it looks like we already have a 1 in the first pivot position, so I'm not going to move that. I'm just going to get rid of the two numbers below it. So for R3, I'm just going to subtract R1. And for R4, I'm going to add 2 times row 1. So the first row doesn't change. The second row doesn't change. Take row 3 and subtract the top row. You should get 0, negative 1. What is that? Negative 3 plus 2, which would be negative 1. And then for R4, if you double the top row and add it to the bottom, you should get 0. Negative 8 plus 6 is negative 2. 2 minus 4 is negative 2. Now, bringing back a shortcut we talked about in a previous video, when I look at rows 2, 3, and 4, so row 2, row 3, and row 4, you might notice that R2 and R3 are pretty easy to see. R3 is just the negative of R2, which means they are multiples of each other. Likewise, R4 is negative 2 times R2, and it's also positive 2 times R3. So what you notice here is that R2 through R4 are all multiples of each other. And from our talks in a previous video, once you can show me that all of the rows are multiples of each other, or if a certain number of rows are multiples of each other, the most bottom row goes to all zeros. In this instance, since three of them are multiples of each other, then the bottom two rows would go to all zeros and the one on top would remain the same. So this would just turn into 1, 3, negative 2, 0, 1, 1, 0, 0, 0, 0, 0, 0. And that is the echelon form of this matrix. Unfortunately, you were only able to get a pivot position in row 1 and in row 2. So when I go back to answer my original question in does the three vectors span R4? The answer is no, because A does not have a pivot position in every row. I don't need you to quote theorem numbers to me, anything out of the book. As long as you give me the brief explanation, like I said, you've made your case to show why the answer is what it is. So that ends the video on section 1.4, Introduction to the Matrix Equation. In the next video, we will jump into section 1.5, which is going to be our introduction to the idea of homogeneous equations or homogeneous systems and non-homogeneous systems as it refers to matrix equations.